It is 6 o'clock. Shall we start? Hello and welcome. Thank you so much for being here on time. Are there any questions? Anything? But first of all, can somebody confirm that you can hear me and you can see my screen?
Hear you and see your screen.
Thank you, Logan. Thank you so much. Please ask me questions throughout the lecture. You can type in your question in chat area, or you can directly speak up. So today is our week 11. We will cover 3 sections. Chapter 7.3, numerical integration, and chapter 8.1. Sorry, I have to reopen my OneNote. It does not register for my pen. Okay. Chapter 8.1 and chapter 8.2 about multiple variables. Okay. Functions of several variables. So 3 sections for today. Remember so far, when we talk about the integration, so if I say integration of x squared, so everyone agree this equal to this. And we call this function is antiderivative of f squared. So f squared we use small fx, and this part we use capital Fx. Okay, so capital Fx is the antiderivative of x squared. How many chapters we prepared for the final exam? All chapters. Final exam is comprehensive. The detailed information about final exam will be announced, so stay tuned. Okay, so this is so far we have antiderivative, but not all functions has antiderivative. For example, these functions, okay, you cannot find antiderivative for these functions, because antiderivative cannot be found. If you cannot find antiderivative, how do you do, for example, e raised to power x squared? You cannot do it. Okay, you cannot do it. But we can estimate. We cannot do it. But we can estimate. Okay. For example, if this function is like this, okay, just for example, okay, just for example, we cannot exactly find out integration, but we can, for example, the integration from a to b, and we can divide AB into several subdivisions. And then for each one, we pick a midpoint. Remember before we pick a midpoint of each subdivision. And then we divide into rectangle. So it looks like there's a rectangle here, rectangle here, rectangle here. Okay. So we actually use delta F, then Fi. Fi, Xi is the midpoint. And we add them all. We use this method to estimate. Okay. This is from last class. or 2 class higher. And today, we use another rule for estimate the definite integral. We just approximate the definite integrals, okay? And this rule is, by the way, the one we have used so far is the Riemann sum. Okay, there is a name, Riemann sum. It is in memory of German mathematician Bernhard Riemann. So that is what we have done so far to estimate, how to estimate the integration. And today we'll use another method called trapezoid rule. Trapezoid rule. When we use trapezoid rule, we actually look at this graph here. Okay, there are many this part. This R1 is just, imagine there are many other parts here. We just take one part, for example. Okay, and to calculate this shaded area, we need to have 2 points. One is x0, the other is x1. So fx0 is from here to here. fx1 is from here to here. And we want to find out what is this area. So this area, if we draw a straight line from here to here, it is like trapezoid. And we know the area is this part, so fx1, plus this part, fx0, and this part here is data x. Okay, so fx0 plus fx1 divided by 2 times data x. That is the area. This is the area. Okay, this is the area. And imagine we have many points. We just take x0, x1. Imagine we also have x2, x3, x4, xn minus 1 until fxn. Okay, and then we can calculate the area. There are n trapezoid. So each trapezoid have the length, okay, data x, and then x over 2, and we get this expression. Okay, so this leads us to the trapezoid rule. So this rule said, if you want to calculate integration from a to b, it is roughly, so this is approximately equal to data x over 2. What is data x? Data x equal to b minus a over n. N is number of sub-intervals. And then bracket fx0, 2fx1, 2fx2, 2fxn minus 1, then last item is fxn. So any questions so far? Why do we use this method? Because we cannot find some antiderivatives, so we have to looking for x approximation. Okay. No questions so far. Okay, let's look at example. approximate the value from 1 to 2, 1 over x, using trapezoid rule. If some student said, okay, I can find antiderivative of 1 over x. Yes, in this function you could. Okay, so for example, if we don't have exclamation, this is actually ln x, then 1 to 2. Okay, and equal to ln 2 minus ln 1. And what is ln 2? Okay, use Excel or your calculator. So equal ln opening bracket 2. I got 0.693147. And ln 1 is just 0. Okay, you can use Excel to verify what is ln 1 equal ln 1. It is 0. Ln 1 equal to 0. So as a matter of fact, we can find the exact value of this definite integral. The result is 0.693147. We can find it because we know the antiderivative function. But sometimes you do not know antiderivative function. Okay, so this example to illustrate how to use trapezoid to estimate, to get an estimate of this integral. Okay, so we are going to use this one here. So what is our A? What is our B? A equal to 1, B equal to 2 in our example here. See, this is our A, this is our B. Okay, so A is 1, B is 2. And then how many n? N is 10. Okay, so when you have n equal to 10, so first of all, you need to find data x. So this formula, we need data x. So I will copy maybe the original function here. So we are asked to do this. So, okay, so I'll refer to this rule here. So when you have A equal to 1, B equal to 2, n equal to 10, plug in 2 minus 1 over 10 equal to 1 over 10 or 0.1. Okay, so we found our data x, and then you plug in when n equal to 10, we have 11 points. See, from 0 to n, you have n plus 1 point. Okay. And now what is our x0? And we need to specify what is our x0, x1, x2 until x10. We need to specify those. x0, it is just A. It is just 1. And x1, it is just x0 plus data x. So it is just 1.1. x2, it is actually x1 plus data x. Okay. So it is 1.2, etc. until x10. x10 it is actually b, it is 2. And the one before x10, for example, x9 is actually 1.9. Okay, so basically, if you have this is A, this is B, and you have so this A it is actually x0, this B is xn. Between A and B, you have x1, blah, blah, blah. In this example, we have x9. Okay, you have those points. Okay, now plug in this formula here. So we have delta x, it is 0.1 over 2 times fx0. We know fx0 is 1, so it is just f1. Okay, it is just f1. And then plus 2 times fx1. x1 is actually 1.1. So 1.1. So remember, what is our fx? Our fx equal to 1 over x. This is our fx. Okay, so let's plug in number for this is actually x1 and then f 1.1 plus 2 f 1.3 plus 2 f 1.4 plus the second formula is f2 f 1.9. The last item is f2. So I pause for a moment to see if you have any questions. Okay. So after that, remember what is fx? Fx equal to 1 over x. Okay. So you just plug in. f1 means it is 1. 2 times 1 over 1.1. 2 times 1 over, this is actually 1.2. 2.1 over 1.3 until 2 times 1 over 1.9 and plus 1 over 2. Okay, and now you got to calculate this. So usually I will use Excel to do this calculation. So what I'm going to do, because I noticed there are some patterns, it is 1.1, 1.2, 1.3, it is actually 1.0 here. Did you see 1.0 here? Start with 1.0, 1.1, 1.2, and then automatically generate the number until 1.9. See, okay, until 1.9. So after that, what I will do, so 1.1, 1.2, 1.9. I actually have 2.1 here. Maybe I will do this because most item has 2 times. So I combine this one, the first one and the last one together. So the first one is 1, the last one is 1 over 2. So it is actually 3 over 2. and then copy the rest item. The reason I am doing this, I want to utilize Excel to looking for pattern. So in Excel, I will just focus on this part. I will use Excel. So I combine the first item, last item. Okay, so now I'm going to focus on Excel. So from actually 1.1. Okay, so each time I need two times 1 over this number. So each time, see, I need to do 2 times 1 over this number. Okay, so I need to do this. Then I just copy down the formula, drag it down. So each time I use, okay. So after that, I just add all this number together, Okay, so I do sum, add all this number together, and I got 12.375. $12.37543. So I copy down the got 3 over 2, it is just 1.5, right? And then, and I also have 0.1 over 2. So I need to calculate this. Okay, so what is this? So again, I will use Excel. So equal 0.1 over 2 times bracket 1.5 plus this number. So the final result, I got 0.693771. So this is what I get final result, estimate. When you compare my estimate with the exact value, this is the exact value. Okay, this is the exact value of this interval. They're very close. Did you see that? They're very close. Compare these two numbers. So one is the estimate, the other is exact number. Okay, any questions?
Excuse me, I have one. I just wanted to ask, with the trapezoidal rule, will the x value, say if it gets to x of, when it gets to x of 10, and will it progress similar to x of 0, how it was, where x of 0 equaled 1 and x of 1 equaled 1.1? If it was, say, x11, would it be 2.1? And so on and so forth?
You say if we increase the, first of all, I need to answer the question from the chart. It is 3 over 2 here. See here, 3 over 2. I combine the first item and the last item here. Okay. Return back to your question, Logan. Can you rephrase it?
Yeah, my bad. So with So within the trapezoidal rule, x0 equals 1, and it remains that way until it reaches x10, where like it progressively increases from, we're at x1 equals 1.1 and x2 equals 1.2. If we increase to something like x11, would it be 2.1? And would that similar fashion follow suit for any x values above 11?
Thank you so much. I think I got your question. So
Yeah, sorry.
this example, our integral from 1 to 2, and we are given n equal to 10. This is given, n equal to 10, okay? If this is the case, we need the point from x0 to x10. We cannot go to x11. We can't.
Okay.
The last one is x10 because n equal to 10. If n equal to 11, the last one is 11, but n equal to 10 is given.
Okay.
Okay. Thank you for your question. Any other questions? And the other. Can you repeat equation should be exact value and which would be estimate? Thank you, Riley. Thank you so much. The exact value is here. .693147 from Excel, from round 2 minus round 1. Okay, the exact value is here. Is this number. And what is the estimate value? Okay, the estimate value is here. Our calculation result, this number is the estimate value. Okay. And this also available on the slide here. Okay, so the actual value is this one. The actual value. And the estimate value is this one. This is the estimate. This is the exact value in this slide. Another question, would we prove this on a test without Excel? During the test, unfortunately, I'm not sure if you can. I think you are allowed to use Excel during the test. Can someone confirm that when you did test 1, test 2, can you use Excel?
With test 2, we had we had access to Excel, but I don't think we had it for test 1.
Okay. For final exam, I think you are allowed to use Excel, even it is not belong to external resource. It is just part of the course. It is just like the calculator. You are allowed to use calculator, so you would be able to allow use Excel. Okay. Please tell me the exam in person. Exam is not in person. Exam is online through web assign, the same as we did for test 1 and test 2. I know the registrar's office posted our exam location in June. That will be updated. So the final exam online on web assign. Okay. Okay. And the Excel can be considered as a calculator. Okay, so this simple calculation you can use, if you want, you can use Excel. Okay, any other questions? Okay, so far we actually did trapezoid rule. Trapezoid rule allow us to estimate integral. Now we introduce another rule, Simpson's rule. Simpson's rule. And when we do the Simpson's rule, we use this principle here. So our objective to find the integration from A to B, usually A is x0, B is xn, okay? And we want to divide into subdivision. We want to divide into R1, R2 until Rn. There are n subdivisions with n plus 1 points. 3.1, 0.2, 0.3, etc., point n. Okay, but there are only n subdivisions, so it is Rn, R1, R2, Rn. Okay, when we did it, when we will use this Simpson's rule, we are looking at just take 3 points, for example, x0, x1, x2. Okay, and then we want to find a point, for example, P1, P2. And we could find this rectangle here. So this rectangle plus this rectangle and plus maybe another rectangle so far. Okay. So this could be one way to do it. And this one, actually, this is what we did before, Riemann sum. If you see the rectangle, it is the Riemann sum. We did this last class, okay? And what is Simpson's rule is this. By the way, before we do Simpson's rule, just briefly review of trapezoid rule. The trapezoid rule, you actually do this. Okay, so if you found this area, there is a curve. Instead of this curve, we replace this curve with the straight line. Okay, so we use this straight line, and then we use this fx0 plus fx1 over 2 times delta x. Okay, so this is a trapezoid rule. Okay, use this trapezoid. And the Simpson's rule is actually use a different approaches here. So if we have these 3 points, we take 3 points. Okay. And then we use a parabola. See, this part looks like a parabola from here to here. So we take 3 points. And it is turned out the area under here, what is the area? The area, it is actually delta x. We don't need to prove, we just need to remember this, okay? And times fx0 plus 4 fx1 plus fx2. That's it. So this is the area equal to this area. And where is my f0? See, this is f0, fx0, and this is fx1, and this is fx2. And these 3 points located in a parabola. Okay. So this is just this part. Imagine we have many this part. We have many this part, and each part you just do many. So this is one part. Another part, the first part is 0, 1, 2, then 2, 3, 4, etc. The last one is n minus 2, n minus 1, n. And then we simplify this, get this expression. So this gives us the Simpson's rule. If you want to calculate definite integral, you use Simpson's rule. This is the formula. The pattern is, so coefficient is 4, 2, 4, 2, 4, 2, until 4. And then the last one is fxn. Any questions? No. The final exam is online, not on blog. Yes, the final exam is online, not in person. Thank you, Riley, for your help. Okay, let's take an example. So this question we did using trapezoid rule. Now we are going to use Simpson's rule. So to use Simpson's rule, we just use this formula. So we are going to do 1, 2, 1 over x dx. Okay. So delta x equal to b, b is 2, a is 1, and what is n? With n equal to 10. So delta x equal to 0.1. Okay. Delta x equal to 0.1, you have this is 1, this is 2. So this is x0, this is x10. And then you should have x1, x2, x3, x4, x5, 6, 7, 8, 9, 10. 7, 8, 9, and then this is x10, and this is x0. Okay. So x0 is 1, x1 is 1.1, x2 1.2, x3 1.3, etc. 1.7, 1.8, 1.9, 2. Did you see that? Okay. And then you plug in this formula. Okay, plug in this formula. So it is equal to delta x is 0.1 over 3 times fx0. So means fx, x0 is 1, so f1 plus 4, fx1, so 1.1 plus 2, fx2, it is 1.2. Okay, so 4, 2, and then plus 4. 3, x3, see, x3 is 1.3. So x4 is 1.4, x5 is 1.5, x6 is 1.6. Okay, so we are in x3, then plus 2, fx4. x4 is 1.4. Okay, so 2, 4, then plus 4, f1.5 plus 2, f1.6 plus 4, f1.7 plus 2, f1.8. This time I got to be careful. This is a 4, 2, and then 4. 4, f1.9, this is 4f, and then finally fn, f2. Did you see this? x10 is 2. So any questions? See, this is a long expression. And now I have to then plug in the numbers. So 0.1 over 3, it is 0.3. f1, remember what is fx? Fx is 1 over x. So f1, it is just 1 over 1 plus 4. f1.1, 1 over 1.1 plus 2, 1 over 1.2 plus 4, 1 over 1.3 plus 2. One over 1.4 plus 4, 1 over 1.5 plus 2, 1 over 1.6 plus 4, 1 over 1.7 plus 2, 1 over 1.8 plus 4, 1 over 1.9, and then plus 1 over 2. Okay, so as you can see, I have many calculations. So I better use Excel. As usual, I want to combine the first item with the last item. I want to combine the first one with last one. So I will get, move it here, 0.3. So the first one is 1, the last one is 1 over 2. 1 plus 1 over 2. So 3 over 2, right? Yeah. And then I will copy the rest of the item. I will try to use different, then I will use this part. I will use Excel, the one with the green color. This part, I will use Excel to figure out what is this result, because it has pattern. It's actually up to 0.9. This part, I will use Excel. Okay, so Excel, I will do 1.1, 1.2 until 1.9. Excel. So Excel, I will use 1.1. Here, this is my reference. I need to. So 4 times 1 over 1.1 plus 2. 4, 2, 4, 2, 4, 2. This is the pattern. Okay. Now, try to move so that, okay. Okay, equal. So 4 times 1 over this number. That is the first item. 4 times 1 over 1.1. And the second item, I need to do 2 times 1 over this number. Okay. And the next time, I need to do 4 times 1 over this number. Next time, I need to do 2 times 1 over this number. Next time, I need to do 4 times 1 over this number. And next time, I need to do 2 times 1 over this number. Next time, I need to do 4 times 1 over this number. And then next time, I need to do 2 times 1 over this number. So for 1.9, I need to do 4. I need to do 4 times 1 over 1.9, okay? And then I need to add all these numbers together. So I got 19.29453. So I need to change maybe black color. Okay, so I repeat this number 19.29451 and 3 over. Okay, so this is the number. Now I need to figure out what is this result. Again, use Excel. What is this result? Okay. Okay, so what is that result? So equal this number plus 3 over 2. And the result times the result times 0.3. So looks like I didn't do it correct. I will find out why. Oh, you know what? This is 0.1 over 3. I did this part wrong. So 0.1 over 3 is not 0.3. 0.1 divided by 3, it is 0.0333. I made mistake here. Okay, I made mistake here. So here, I got 0.1 over 3, that is correct. So it should be 0. Maybe I'll keep right 0.1 over 3. Okay. I will keep right 0.1 over 3. I will keep right down 0.1 over 3. And then my result should be this number 19 0.29, that number is correct, okay? It is just times, should be 0.1 over 3. Now I got correct answer, 0.69315. Okay, so this is my Excel calculation, okay? Okay, so we got the estimate for this integral using Simpson's rule. And this result more close to the actual value than the one we used for trapezoid rule. Okay, so that concludes our session 3 of chapter 7. Take a break. We'll do chapter 8, session 1, and session 2, functions of several variables. Okay. Not sure this lecture is being recorded. Yeah, hopefully it's recorded. Okay, guys, take a 10-minute break. Come back at 7:03. Kiss you. Thank you so much. You are correct. Thank you. So break. Back at 7:03. All right. Any questions? Okay, before the break, we did the Simpson's rule. We did this question. Now, one more item, then we move on chapter 8. This is still chapter 7, section 3. So this one is error analysis. This table shows the bounds on error terms incurred when used the trapezoidal rule and the Simpson rule. Okay. So suppose we want to estimate the integral a to b fx. The maximum error occurred when used trapezoidal rule is this expression. M is a number such that the second derivative, the absolute value of second derivative, smaller or equal to m for all x in AB. And when you use Simpson rule, this is the expression. The maximum error, m, is the fourth derivative, the absolute value of the fourth derivative, smaller or equal to m. Okay. So let's take a look at the example. Find the bounds on the errors incurred when is approximated using A, trapezoidal rule, 2, Simpson's rule. Okay, question A is also n equal to 10. And compare this result with the actual errors. So how do we do this? So we use this formula. So in this formula, so this is question A, this is question B. Okay, question A, trapezoidal rule. Question B, Simpson's rule. For which function? For 1 to 2, 1 over x dx. So obviously, n equal to 10. So we know this n. So b minus a equal to 2 minus 1 equal to 1. We know b minus a. The only thing we don't know is m, capital letter M. Okay, so what is m? M is a number such that the second derivative smaller or equal to m. So we need to take second derivative of fx. So remember what is fx? Fx is 1 over x. Okay, so let's do second derivative. To do second derivative, we need to do first derivative first. Okay, so the first derivative, remember when you have xn, derivative n xn minus 1. Okay. Just check the message. Any questions? Okay, so what is the derivative of x raised to power negative 1? So it is negative 1 x negative 1 minus 1. So minus 2. Okay. So negative 1, just delete negative 1. It is just a negative. So this is the first derivative. Now second derivative. So take derivative, you have negative. So negative 2, x negative 2, negative 1. Okay, so negative, negative, positive, negative 3. Okay, and this function I can write down 2 over x raised to power cube. So this is our second derivative. The purpose of finding second derivative is to find capital M. We want to know this second derivative smaller or equal to which number. Okay, so to do that, recall that what is the x value? X changed from 1 to 2. So x is between 1 and 2. It could be 1, it could be 2. Could be anything between 1 and 2. Okay, if this is the case, I use 1 over x. It must be smaller or equal to 1 over 1, greater or equal to 1 over 2. This is also hold true. Okay. And then I take a cube. It is still called true. Okay, and then I move this cube to the bottom. Okay, and after that, I times 2. It is still hold true. Okay, the reason I am doing this, I found out this. What is this? 2 over x cubed. It is a second derivative. Second derivative. So this is a second derivative. And I found second derivative smaller equal to 2. So I found capital M. Capital M is 2. Here, second derivative smaller equal to which number? I found capital M. Questions? Okay, so once I found capital M, I plug in this formula. Just plug in this formula. So I'll copy the formula here. So question A, the formula said it is MB minus A over 12N squared. Okay, so M is 2, B is 2, A is 1, N is 10. So I need to find this number. Okay, so it is just 1 over 6 times 10. So what is that number? One over 6 times 100. 0.001667. Okay, so I found the bounds and the errors. This is my answer. Questions? So this is one way to find capital M. Another way to find capital M is to plug in the second derivative function into algebra to draw a diagram. See, this is the second derivative, actually f second derivative equal to this function. And then looking from 1 to 2, this is A, this is B, 1 to 2. And you go up, okay, and you found this maximum value here. So this is M equal to 2. This is another way to find M. Okay, so just let you know. Okay, we did question A, trapezoid rule. Now do question B, Simpson's rule. So to use Simpson's rule, we need this formula. We need to find out the fourth derivative of fx, and then use this expression. Okay. So we need to continue. So we found the second derivative. Now found the third derivative. So the third derivative, use this. Okay, this is second derivative. So 2, -3, x, -3, -1, -6, -4. Okay, this is the third derivative. Now fourth derivative. So take derivative of this. So -6, -4, -4, -1, 24, x -5. Okay, and then I rewrite it to 24 over x +5. Any questions? The purpose, we found the fourth derivative. We want to find an M. We want to see this fourth derivative smaller than what number? This M. Okay. Okay, now to find this M, we know x is between 0 and 1, and 1 over x must be between 1 over 2 and 1. Okay, and then we take fifths. All the part we raise to power fifths. It is still true. Okay, and then we have 1 over x fifths smaller than 1, and this part is 32. So after that, we multiply 24. Why multiply 24? Because the fourth derivative has 24. Okay, so 24 here, 24 here, 24 here. The inequality still hold true if you multiply a positive number. Okay, and then what is this? This happened to be our fourth derivative. So we found the fourth derivative smaller or equal to 24. So our capital M is 24. Okay. Any questions? Once we found our capital M, we use this formula. So it's 24. B is 2, A is 1 raised to power fifth over 180 times N. N is 10 raised to power 4. So this number equal to 24 over 180 times 10 raised to power 4. So we need to find what is this number. Excel. (24 over 180 times 10 raised to power 4). So this is this number. So what is this number in decimal? So this number in decimal is 0. Okay. So this Excel is scientific notation. Okay, it's the same as this number. Okay. So let's conclude section 3 of chapter 7. Okay. Any questions? Now we move to chapter 8. Chapter 8, functions of several variables. So far, we have y equal to fx, just one variable x. Okay. If you have another variable, x and y, so we are going to use z equal to fxy. So we have two variables as independent variables. So this is the concept of this chapter. And sometimes we also have maybe 3 variables. This is 2 variables, but our textbook focuses on just these 2 variables. Okay. So example. So if we have fxy equal to this, compute f00, f12, and f21. Did I maybe jump something? Functions of 2 variables, yes. Okay, let's do it. So f00 means you plug in x is 0, y is 0. Okay, x is 0, y is 0, and you got final result 2. And fx12 means x equal to 1, y equal to 2. Plug in this equation. And the next one, x equal to 2, y equal to 1. Okay. So this is a function with 2 variables. Now let's take a look at what are the graphs looks like for functions with 2 variables. And this is a XYZ plane. Okay. you have actually point in this. We have point A, B, C, D. So how do I locate point A? Point A said x equal to 2, y equal to 3, z equal to 4. So I locate, this is my x equal to 2. So x, this is 0, x equal to 1, x equal to 2 here. And then y equal to 3, this is y, this is 1, 2, 3. Okay, so x equal to 2, y equal to 3, it is here. This point represents x equal to 2, y equal to 3. And then z equal to 4. This is z. Okay, this is 1, 2, 3, 4. So the final point for A is here. This point represents x is 2, y is 3, z is 4. Okay, give me 1 second, I'll grab water. Okay, thank you. Any questions? Okay, so the graph of two variables, see, this is z equal to fxy, what it looks like? Looks like this one, this part. This represents z equal to fxy. Okay, if you project this curve into just xy plane, looks like you got this. If you project, okay, and those are very beautiful dynamic curves generated by computer using two variables. So the first one is this one, and the second one has cosine function, and C has the exponential functions, D has the logarithm functions. Okay. Now an important concept, level curves. Level curves, we can visualize the graph of function with two variables by using level curves. So if we have this function z equal to fxy, if we use a plane, see this pink part, if we cut, and then project it to xy plane, and you got this. Okay. So this level curve C, this C, is with the equation fxy equal to k. So this plane is z equal to k, projected to xy plane. Okay. If only look at y plane, it is this. So definition of level curves. The level curves of a function of two variables are the curves with equation fxy equal to k. K is the constant in the range. Okay, so now let's look at examples. Sketch a contour map for function. So what is a contour map? Let's look at the definition here. what is the contour map? By drawing the level curves corresponding to several k, we get contour tool. So we need to take several different values for k. Okay. Now look at this example. Sketch contour map. So we need to take several different values for k. Okay, so why we are picking those numbers? You actually can pick any number. Okay, those are just examples. The reason we pick those numbers is because this is the square. So we tend to pick, 1 square, 2 square, 3 square, 4 square, etc. We take those as the k. So when k equal to 0, we get this, k equal to 1, k equal to 4, etc., etc. So to sketch, we get this picture here. K equal to 0, k equal to 1, k equal to 4, k equal to 9, k equal to 16, so those are the contour maps. And this one is a sketch the graph. So how do you sketch this graph? Because we get this idea over here, so we know, so if k equal to 0, and then k equal to 1, maybe this, k equal to 4, k equal to 9, k equal to 16, something like that. If you press it, if you press this, you get this layout here. If you expand it, and this is the sketch of z equal to x squared plus y squared. Okay. Questions? All right. So the level curve has applications in weather map, the weather, the temperature, the latitude. Okay, you can read all about yourself. Okay, that concludes session 1 of chapter 8, functions of several variables. Now we go over session 2 of chapter 8, partial derivatives. The partial derivatives. Remember now we are dealing with two variables, x and y. So the first partial derivative with respect to x, we use this simple partial derivative. Okay, so df dx, it is just a limit when h goes to 0, fx plus h, y, then minus fxy. Similarly, the derivative relative to y, it is this function. So when you take the derivative relative to x, you consider y is constant. When you take derivative relative to y, you take x as constant. So let's take example. Find the partial derivative df dx, df dy of the function. So let's df dx. df dx means you only take derivative relative for x. Take y as constant. Item derivative x, it is 2x. The second item, take y squared as constant, only take x as derivative. So it is this. The third item, constant derivative is 0 because y is constant. So this is the final result. Okay.
Would it also be plus y cubed? If y squared stayed, would y cubed also stay?
Thank you for this question. We are doing the derivative relative for x. We only take derivative relative for x. We consider y is constant, so this would be 0 because y cubed, it is like, so if I rewrite this expression to x squared minus x b squared plus b cubed, b is constant. I want you to take derivative of this function, so you get 2x minus b squared. It is like y squared, and this is constant. The derivative of a constant is 0.
That makes sense. Okay, thank you.
Okay, thank you. So this is the derivative of df dx. Now, df dy. dy means you only take derivative for y, only focus on y is variable. Consider x is constant. X is constant. So x squared, constant derivative 0. And only take derivative relative to y. Okay, so you got x constant. And y squared is 2y. And the last item, take derivative of y is 3y squared. So the final result okay. So we take the derivative and now answer this question. We found the partial derivative. And now what is the rate of change in x direction at point 1, 2? Answer this question. So this question is the same. The rate of change at x direction means df dx. Okay. When x equal to 1, y equal to 2. This is x is 1, y is 2. So equal to plug in this expression. When x is 1, y is 2. So 2 times 1 minus 2 squared. So this is the rate of change. Questions? Okay. Question, what is the rate of change in y direction when x equal to 1, y equal to 2? So we need to use this expression here. So df dy equal to when x equal to 1, y equal to 2. So plug in x is 1, y is 2. Okay. Any questions? Okay. Cobb-Douglas production function, very important function in economics. So if a function has this format, A and B are positive constant, and this function called Cobb-Douglas production function. The partial derivative to x is marginal productivity of labor, so x related to labor, and y, the partial derivative of y is marginal productivity of capital, so y usually represents the capital. Okay, let's take a look at the example here. A certain country's production function in early years following World War is described using this function. X is the unit of labor, Y is unit of capital. So question A, compute Fx, Fy. Okay, compute Fx, Fy. So Fx means df dx means you only take derivative for x, consider y is a constant. Okay, so remember x derivative x minus 1. So consider y is constant. Y is constant. Only take derivative of x raised to power 2 over 3. So use this formula. So 2 over 3 x 2 over 3 minus 1. Okay. This is constant. You combine constant. So it is 20. Okay. And then y 1 over 3 x negative 1 over 3. And then you can move negative to here 1 over 3. Questions? So this is A, and then Fy means df dy means you only take derivative for y, x is constant, so only derivative for this part. Other part is constant. So 30x 2 over 3, this is constant. And for this y, you use 1 over 3 y minus 1. And again, you have 10. This constant is 10. X 2 over 3 y negative 2 over 3. So it is equal to 10 x over y bracket 2 over 3. Okay, any questions? So we completed question A. Question B. What is marginal productivity of labor and the marginal productivity of capital when the amount of labor, so when x is 125 and y is 27. Okay. So you just plug in x 125, y 27 here. So when x when x is 125 and when y is 27, you figure out what is this number. Okay. And this is a two-liter calculation. This is 12. And again, when x equal to 125, y equal to 27, what is this number? So this number is 27, then 7 over 9. Okay, so we finish part B. And part C, should government encourage capital investment or encourage labor? So obviously, the marginal production for the investment is 27, and the marginal productivity of labor is 12. So the government should invest capital because the marginal productivity is higher than the marginal productivity for labor. Okay. Questions? Okay. If you are economics major, you know the substitute commodities, complementary commodities. Okay, so the supplement. So what is the substitute? If you think about coffee and tea, those are substitute. And what are complement commodities? Think about automobiles and tires. Okay, and how do we know mathematically there are two commodities A, B are substitute? So if both greater than 0, the partial derivative, they are substitute. If both partial derivatives smaller than 0, they are complementary. Okay, take a look at example. Example 5. Suppose daily demand for butter is F, PQ. Daily demand for margarine is G, PQ. So PQ represents the price per pound for butter and margarine. Okay. And XY, so this is X, this is Y, is millions of pounds. So determine whether those two commodities are substitute or complement. Okay, so how do we know substitute or complement? Take partial derivative. If both partial derivative greater than 0, substitute. If both partial derivatives smaller than 0, complementary. Okay. So this is our F function. This is our G function. Take partial derivative F. Take partial derivative for Q. Okay. So F partial derivative Q. Why we need a partial derivative for Q here? So F partial derivative Q. Okay. Derivative for P. So we figure out F take derivative of Q. So when you take derivative for Q, consider P is constant. Only take derivative for Q. Okay, everything else is constant. So this becomes this because P is constant. Okay. And next for G, you take derivative for p. Here, for g, take partial derivative for p. When you take derivative for p, just take derivative for p. Q is a constant. So just get 2 over 1. Okay? So do you see this is p squared always greater than 0? This is square root of q always greater than 0. So we get both positive. That's why margarine and butter are substitute. Okay. They are substitute. Questions? We don't take second break. We keep on going. Then we finish the lecture. Hope that works well for everyone, because we just have one example left. Okay. Okay, so we did that part. Now last example. Second order partial derivative. Okay. I'll try to find the notation. Okay, so let's do first order first. So what is f partial this? So when you do x, consider y is constant. Only focus on x. Everything else are constant. So x cubed, 3x squared. Okay, x squared, it is 2x. Y is a constant. 3x is just 3. Y squared is constant. And the constant derivative is 0. This one derivative is 0. Okay. So I got the first derivative. Now, do derivative for y. Maybe I need to simplify this one. It is just 3x. Okay. Now do the y. When you do the y, only take derivative for y. X is a constant. X is constant. So this is 0 because it is constant. And this only do derivative for y, you get negative 3x squared. And this derivative for y is 2y. Did I miss something? I missed this y here. So derivative of this y, it is actually 3x, 2y. Then derivative of y squared is 2y. Then simplify, I get this is the first order. The second order means let me double check the notation. The second order means df df dx. Maybe I will write down simple. This is the second derivative, means once you get this first derivative here, this is df dx, then take derivative relative to x again, you get this. For this, take derivative relative for x. Consider y constant. Okay, so I'm going to write down d then dx. That is the meaning of fxx. Okay, so consider y constant. Just take derivative of x. So you got 6x minus 6y. That's it. Okay. Questions? And now fyy means, see, this is the derivative for y. Then take derivative for y again. dy of this expression. So negative 3x squared plus 6xy plus 2y. Okay, so only take derivative for y. X is constant. So you got 6 plus 2. 6x plus 2. So this is fyy, second derivative. Another possible is fxy. So fxy means you take derivative of, let me see, fxy. So take derivative x first. So you got this one here. First order derivative is here. Take derivative of x. So take first derivative x, you got this. And then this, take derivative of y. So this is the meaning of fxy. Okay, so only take derivative for y, x is constant. So you got and the last one, fyx, means take derivative for y first. This is derivative for y, so copy down this expression. And this, take derivative of x. Okay. So only take derivative for x, y is constant. So it goes 6x. Okay, those are the second derivative. Which one? This is second derivative, second derivative, second partial derivative, second partial derivative. All right, that concludes the lecture part. Are there any questions? Anything? Remember, you need to practice a lot to be comfortable with the content. I would suggest you redo the examples in class and then do examples in the textbook. Do example many times until you feel comfortable. You can complete the example without looking solutions. Okay. Any content questions, do not forget Mathematics Learning Center every day. Somebody is there. Of course, you can email me for specific questions. Okay. Next week is our last lecture. Hope we'll do some review next week. Okay. Any questions? Okay, that's all for today. Thank you so much. See you next time. Bye.
Thank you.
Thank you.
Thank you.
Thank you. Bye.